videos afterwards. Excellent, excellent. Okay, good. So for the other students who have not been showing up now, I just wanted to make sure that we have. Okay, Isabel, you are also forming your project now. Okay, so I'm now I would like to have you be ready, be in the process of preparing your final project's topic, and then you can talk with me regarding to the appropriateness of the project, and then I can help you, I can comment for you, I can give you my advice and other possible resources, all the available resources and reference relevant to your project. I will tell you that, okay, and then that will help you to improve your project. Then you have about 10 days, about 1 week for the midterm exam number 2, that you will present your project, present their importance, and then also present your specific aims for a project. How will you do the research to advance that topic, right? So I want you to start prepare earlier. So right now I have mainly Trenton and Isabel. Two of you, Isabel, you will work by your own, right, Isabel?
I think so.
Okay. So Trenton, you can find other students available to work with you. I think we have also other students. They want to join the other classmates as well. So they actually watch the video after the class. So you can either talk to them and find a project together, or you can work by yourself. It's also fine. Okay. Trenton. Yeah. Okay. Good.
Okay.
Yeah. So for all the students who are not in the Zoom now, please let me know your team and your research topic. Okay. So far it seems we have seven teams. Okay. So I will organize your time in the class for the October 30th and November 1st. I will make sure that you all fit into those two classes. Then you can give the lecture, give the seminar. Yeah. Okay. Good. Okay. So I will show you once you show me the team members and the topics. I will organize the agenda and then share to all of you. Okay. Good. Okay. Do you guys see my shared screen on the presentation mode? Do you see it in the presentation mode?
Yes. Yes, we do.
Yeah. Yes. Okay. Good. That's great. So now, let's get started for today's class. Okay. Good. Now, logistics are the same as before. We do have some new things will come, but right now, most important thing is this midterm exam number 2. This actually is a great chance for all of you to practice how to develop the research project, how to create ideas for your research project, and then how to present your project to convince your peers. Okay, and then also how to digest the criticisms, comments from your peers, from your advisors such as me and other professors, then collectively to improve your project. Okay, in the future when you become researcher, research leaders in the academia, like either in the universities or in the national labs, you will always need to develop a new research project and then present that to the funding agencies, to your administrators, to convince them your research is really significant. Okay, so this will occur again. So right now it's a great chance for you to practice it. Okay, so make sure, cherish this opportunity and use it well. Okay, so for the midterm exam number 2, after your presentation, please send me the written proposal. I will comment on that and send it to each group. Okay, I will comment on each group, just send me one in written. Okay, follow the format I have showed in the previous slides, previous lectures. Okay, and then I will comment on that, and then you can use that to improve your project, both your PPT and your model derivation or your experiment plans. Okay, then in the December, you can send me the final report and the final presentation PPT. Okay, and then give the final presentation as well. Yeah. Okay. So so far it seems we are okay with the team members. So yeah. So I will fill up the rest topics once Yibo, Trenton, and Isabel tell me that. Okay, and the rest of other students. Then we will be done with this schedule. Okay. Okay, that's all for the logistics. Now let's get started to our today's materials. So in last lecture, we actually started to talk about the important experiment techniques that can be used to measure the diffusion coefficient. Also can be used to quantify the diffusion process, right? So we list 3 methods here to talk, but right now there are many other methods also available. Okay, so we talked about the first 2, single molecule tracking and the FRAP experiment. Okay, that is fluorescent recovery of the photo bleaching. Now we are going to talk about the last one. It's called the fluorescence correlation spectroscopy. This is called FACS, FCS, FACS. Okay, it's different from FACS. That is flow cytometry. That's different. This is called FCS, FACS. Okay, so this is the first one. The second one is third. Yeah. So for this FACS, for this method, it's actually based on a very clever idea. Do you guys hear me?
Yep, we hear you.
Yeah. Okay, good. So this is actually based on a very clever idea. the goal of the research here is people want to find out that if I have many particles in the solution, I want to know those particles, or actually some chemical. Okay, all the chemicals are made of particles, molecules, right? So people want to know what is the diffusion rate of those molecules, of those chemicals, right? So to measure the diffusion, you will need to one method we talked earlier. Method one is we look into the moving trajectory of this particle in the 2D surface, 2D volume, right? So we want to see how it moves, and then measure the MSD, mean square displacement versus time, and then we can calculate. That is the good method. But that method also has a limited throughput. It also requires expensive high-speed camera to measure that. Okay, so if there are alternative way, use less expensive equipments, then it is more desirable for the lab that just started, for the small lab we just started the work. Okay, so this FACS method actually is one of that kind of experimental technical that is preferred by the lab. It's very simple but very profound, okay? Because it uses both the idea of fluorescent imaging as well as the statistical analysis. Okay, so basically this method actually is taking advantage of the factor that when we use a microscope, when we shine the laser to the volume, it actually, the light occupy a small amount of volume. Light beam occupies small amount of volume, and then if we put those molecule of interest that also can be fused with the fluorescent dye. Okay, so this is called using the synthetic chemistry. You can fuse any molecule with a small molecular fluorescent dye. That dye is too small, that it cannot increase the weight of the molecule too much, but it can give the molecule visible capability. So then when this fluorescent, when this laser beam, you see my mouse? You see my mouse? Do you guys see my mouse?
Yeah.
Yeah, okay. When this laser beam, thank you. When this laser beam inject upwards, this laser beam actually form a cone, okay, form a cone, which is wider at the output of the microscope objective, and then thinner at the focused point, okay, and then diffuse again. This is called converge, and then diverge again. So this becomes two cones head to head, line together. Okay. Now within this cone, and also because this focus is never a point, as I mentioned before, they have a diffraction limit, right? So light will diffract. Light is wave, it diffract. So at the focus point is never a real point. It's actually several nanometers size. Okay. So that gives a very good, very confined volume within covered by this laser. And then the people can generate two transparent, people can use two transparent glass slide to enclose a droplet of the liquid that contains the chemical to be analyzed, okay, inside. And then put that droplet within between these two glass slides. So then these two glass slides actually confine the movement of the molecules, so that the molecule is doing a quasi 2D diffusion. When those molecules diffuse, they will jump into this light volume, right, and then stay inside for some time, and then go out, and then another one is going, okay, depending on how dense is the chemical, the number of the molecule simultaneously get in and simultaneously stay in within this light beam can be changed, right? Now, once they get in, once the fluorescent molecule get in, then they will be excited by this light and then emit out the emission photon. That photon can go through the objective, sun objective again, and then collected by a light sensitive device. I'm saying this method is simple because in this case, you don't need a camera. Camera has a 2D chip. Then you can capture the phenomenon within a 2D plane, right? But in this case, you don't need. In this method, you can use a photodiode, okay? Photodiode that only has 1 pixel of the camera, 1 pixel of the camera. Every camera chip actually has many pixels. Every pixel it is light sensitive. For this case, they only need 1 pixel because all the data you need is the light intensity from this point that occupied by this light beam. Okay, so once the fluorescent molecule get in, then the light intensity increase inside, and then that photodiode, just 1 pixel photodiode, can acquire that photon, and then the intensity goes up, increase. If the fluorescent molecule go out, diffuse outside of this beam, then there's no light source inside this light beam. Then the counting from that photodiode, that PD, decrease. Okay, so then, and the photodiode is usually cheaper than the camera because it's only 1 pixel, right? Only 1 diode. Now, then all we collecting is we keep collecting the fluorescent intensity fluctuation within this light volume, within this volume. Okay, so then we will get some results like this. Do you see my mouse? Do you see my mouse?
Yep.
Yeah. So we will get the intensity change collected as a function of the time, Okay. So this looks very noisy. So if the fluorescent molecules are large, then you will see many of these lines. You see many of these lines combined together. Each line actually is one molecule get in. Okay, they go up, and then there are many lines, means many of them together. And here is the mean value. The mean value means there are some molecule, always some molecules inside, not always inside. Actually, it's at any time point, always a certain number of molecules can be counted here. They are not the same molecule. So 10 get in, 10 get out. But when that 10 molecule get out, another 10 get in. Okay, so it's a dynamic equilibrium. So that is the mean value. Okay? The mean value. And then sometimes at some moment, more molecule in, at other times, less molecule get in. That's why they have some fluctuation up, above mean, or below, down, below the mean, right? That's the reason. Now, this is a super useful curve. It looks so very random, but this contains a lot of information, okay? So we will talk about this, and also this curve. We have a homework to relate to this correlation curve, okay? So once you get this kind of results, this kind of curve, you can calculate not only the diffusion coefficient, capital D, but also calculate the concentration of the molecule within this solution embedded between two glass. Okay, and also you can calculate many useful things from this curve based on the mathematical principles embedded in. Okay, we will talk about it, like mostly is the Poisson distribution. Okay? That's really useful. Now that's actually the experiment setup and the data we will acquire based on the FACS method. So usually the procedure is you focus a laser beam to a small spot in a diluted solution. That solution is confined between two glass slides. Okay, and then usually solution is 1 nanomole. That is the good number, because at this time you can see the fluctuation very easily. If this is too dense, if it's very high concentration, then you won't be able to see the fluctuation that much, because all the time you have a lot of molecule inside, and the fluctuation you see is actually very little. What we mention, what we mean by fluctuation actually is the variance. Remember when we talk about the statistics, the variance, that is the deviation from the mean, right? The variance as a function of time. So you want that variance so that you can calculate the properties of the molecule easily. Okay, and here is what I just said. As the molecule move in and out, there are fluctuations. Those are the fluctuations on the number of fluorescent brightness, means the intensity here, fluorescent intensity. Okay. Now this is the basic principles of it. And then the reason people design this experiment is this process, the molecule diffuse into this beam, light beam. This process is a random process, and they match with a statistical process called Poisson process. And that process has a mathematically derived formula to describe it. It is a distribution. It's called Poisson distribution. And by looking at this fluctuation, you will find that if the mean number, this is very important, if the mean number of the molecule inside this spot, within this light spot, is n, you have n molecule inside, okay, n molecule. Then you do this experiment, you take the intensity fluctuation. This fluctuation value is actually equals to square root of n. This fluctuation, what I mean is the square root of variance. Okay, this is the standard deviation. Standard deviation is the square root of n. Okay, this is based on the Poisson distribution. Okay? So let me explain to you what is Poisson distribution. That is the mathematical principle embedded in this method, and will be very useful to analyze those data. Okay, so Poisson distribution was developed by the mathematician Poisson. So he actually studied a random process. So and then find that a random process can be described by a distribution function. Later people call it a Poisson distribution. Specifically, this Poisson distribution is actually a discrete probability distribution that can indicate or can express or can calculate, can express means explicitly using the equation to express the probability of the number of the events occurring in a fixed period of time. Okay? If those events occur with a no average rate, if the average rate of the events occurs, okay, and also those events are independent of the time elapsed since the last events. So this independence means that there are no memory. There are many events happens, but they do not remember each other. The events has no interaction, no crosstalk. Okay. So this is the original description of the Poisson distribution. Okay. What it means is, if there is an event, if there is a series of events, they happen with a average value. They can happen at a different time point. They are randomly happen. But on the average, people knows on average it has a occurrence frequency. Occurrence frequency is mu. Okay. Then the number. This is the average value, but the real value can be changing, can be less than this value or larger than the value. Okay. So this probability is talking about the probability of that real events happens. What is that probability? Okay. So on the right hand side, showing a picture, showing a distribution of Poisson distribution. Here, M is the real events. Okay. So in the top, what we see is if a series of events they happen with the average rate 1, then what's the probability when this happens? Average is 1. What's the probability if we get them at this value, get 0 times, or get 1 times, or get 2 times, get 3 times, get 4 times? Okay. So the highest value is close to 1. Okay, because this is the average value. But it can also happen 2 times, can also happen 3 times. But their probability is lower. Now, if you go to even higher, 3, 4, 5, then the probability is very, very low. Because on average is 1. You're 2 deviate from the average value, then the probability is very low. Okay. So the y-axis is the probability. X-axis is real, how many times happens. Then that's what we are interested in. Okay. Now, if a series of events they have an average rate as 5, then 0 times happen is very low. 0 times happen very low. 1 little bit higher, 2, 3, 4, 5. 4 and 5 around this value is highest because it's the average value. Okay, and then go to 6, 7, then even lower, much lower. Okay, and then if you have 10, average value is 10, then very likely it's 10. But they have a distribution. They are not always 10. Okay, so that is called a Poisson distribution, random distribution. I will give you one example, then you will understand it much better. Now, the contribution of Dr. Poisson is he derived the equation to describe this process. So he found that this process actually can be written in this mathematical derivation. So the distribution of the real event M for a series of events that has the mean value mu. Actually, the probability is the mu to the power of m divided by m factories, and then times exponential to the power minus mu. Okay, so mu is constant. For a series event. They have a mean value, expected value. But if in reality, if we get a 0, what's the probability? Then we put a 0 into the m, and then we calculate this PM. Okay, if we get a 1, then we get for the real events, if it happens 1 time, then we put a 1 time in, and then calculate this. Then P1 is the probability you will get that event happen for 1 time. Okay, and all those events are independent from each other. They are random. They are all random. Okay, and then if we add all these possible events together, real events 0, 1, all the way up to infinity, add all them together equal to 1, because that is the the overall possibility for the events, right? This can be proved. So if you add this value in, you can calculate this. You will find that this is a normalized probability distribution. Then it will equal to 1. Okay. Now, do you guys hear me? Do you guys hear me?
Yes, we hear you.
Yeah. Okay, good. Now, let's give one example so then you will understand this better. So this is one example. Imagine there is a undersea cable. So this is the cable, undersea cable there. So those cables are used to transmit messages, right? Informations. Now, those cable, they are actually contain defects. They always contain defects when you fabricate those cables. And then those defects can occur at different lengths, different parts of the cable. And when this cable coming out from the manufacturer's hands, by characterize those cables, we will know what is the average defect number in the cable. How many defects in the cable? We will know that. Okay, but we do not know where these defects happen inside the cable. That we do not know. Based on the quality control, people wanted to know that how we actually people don't care where is the defects in the cable, but people wanted to know how many defects in the cable. If more defects there, then the cable is not in high quality, right? So we want to calculate that. So the way to calculate it, and calculate it, actually you can use the Poisson distribution. So here is one question, that is that if we know that the defects is on average of 0.1 defects per mile, okay, that's a very good cable, 0.1 defects per mile, then what is the probability? What is the probability that no defects appear in the first 2 miles of the cable? Okay, want to calculate this probability. Now, this is a Poisson distribution. Only thing different here is I convert the time to the space. Right? In the previous, I was talking about a series of events, so that happens in the time. Now, this is the defects happens in the space, but this is the same thing, same mathematical foundations. Right? So now this is a Poisson distribution problem, and we can use the Poisson distribution equation to calculate this. We know we want to know the probability that has no defects in. That means we want m equal to 0, and then we also know what is the mu. Mu is this value. Okay. Here we are talking about what's the in the first 2 miles of the cable. So then the mean value is 2 miles times 0.1 per mile. So then the mean value is mu is 0.1 times 2.2. Okay. And then we want to know this event, m equal to 0. Okay. No defects. Then we can directly use the Poisson distribution equation. Mu is the mean value for the 0.2. Okay. So add in. And then m equal to 0, add in. Then we can calculate this, add the value in, then we can calculate the value. Called about 82% chance that the first 2 miles has no defects. Okay, so that's actually pretty high. If you want to calculate the first 3 miles no defects, then this mean value will increase. M remains the same. Mu will increase, and then this probability will go down. Okay, then keeps going down if you increase the mu. Okay, because the average, on average, the defects, the defect density will keep increasing, and it will be very hard to get 0 defects when you add more and longer fiber cables into the consideration. Right? So this actually is a great example to show what is Poisson distribution and how to use that to calculate the situation in some event that we cannot predict what the exact value is, but we know the mean value. Okay, then we can calculate that. This distribution also used in the used in the gamble. People want to do the gamble, and that mean value you know, but you want to calculate the exact success rate within certain lengths of the time. Okay? So that's also applied. We can also use the Poisson distribution. Now, if we have that equation now, then we can do the same thing as we did before, right? We can do the previously we derived the binomial distribution. Then we can use we can calculate their mean value, variance, standard deviation, different orders of the variance, right? So for the Poisson distribution, we have this value, we have this equation, and then we can calculate the first moment. Then we can add, first moment is actually the m, right? Here we cannot do the integration because this is a discrete 0, 1, 2, it's discrete. Then we can do the adding to do the summary together, right? So then we measure the mean of the m. Then it's the mean m times m is expected the exactly occurred the situation, right? M times probability, and then summing them together. This is already normalized. Then you add some together, and then you calculate this, and then calculate further simplify it, and then we will find this value actually equal to mu. So that is the means this mu is the mean value. Okay. In the same way, we can calculate the second momentum, right? Second momentum, we can calculate. Usually people use m. Usually people use m times. Usually use this one. Usually use this m square mean, and then you can separate this into two. One is m times m minus 1, another is m. This is a mathematical trick. You can separate two and then calculate each one because m mean we already calculated here. So then if we calculate this guy, then we can calculate the m square mean, right? So then for this term, m times m minus 1 mean, then it's here, and then you add them into the derivation, and then you calculate this. You will find this actually is mu square. It's mu square. Okay. Then this is the second moment. For the variance, as we learned before, variance actually is equal to the second moment minus first moment square. So then it is mu square plus mu minus mu minus mu square here. Then we get a mu, right? So this mu equals to this variance. So this actually is a very unique property of Poisson distribution. The variance equals to the mean. Okay? And then remember, variance, square root of variance is standard deviation, right? So that means the standard deviation. Once you know the mean, you also know the standard deviation. Okay. Now, this random distribution also very useful in the in the imaging. So when we do the optical imaging, we actually use the camera chip to acquire the photon emitted out from the fluorescent molecules. For in the FACS experiment, you actually have a photon dyed PD to capture how many photons emitted from the fluorescent molecule, and then you can derive that fluctuation curve, that green curve I showed in the previous slides as a function of the time. In that process is Poisson distribution. It is similar when the photo dyed to capture the photon is similar to the hand to capture the rain. If there's a raining day, there are many water raining droplet coming out. The raining droplet has its average value. Okay, it has an average value. Then you put a hand out for a certain time. You expose your hand outside of a window for 5 seconds, 10 seconds, 20 seconds, or 1 minute. The number of the rain droplet collected by your hand is also following the Poisson distribution. Okay? It's the same thing. And that is similar to the photodiode, the photosensitive pixel I just mentioned. The photosensitive pixel collect the collect the photon coming out of from the fluorescent molecule in that light beam, right? It's the same. So this is since this is a Poisson distribution, then based on that we can know what is the signal and what is the noise. What is noise? The signal actually is the mean value you will get from the molecule. That is n. Okay, that is n number of molecule inside the light beam. The noise is that fluctuation. That is because some molecule get in, some molecule get out. And then they also give the light fluctuation. And their light fluctuation is the variance here. It's the variance here. We calculated this variance. Square root of variance. Okay? That is the noise, square root of n. Then signal to noise ratio means the signal divided by the noise is n divided by square root of n. Then it equals to square root of n. Okay? This can be tested. If you do the imaging in different speed. For example, we have high speed image, 600 frame rate per second. That means every 1/600 second, you will take one frame, take one picture. Okay. Then the exposure time is 1/600 between the frames, right? If you go to the slower frame rate, like 10 frames per second, then the exposure, you take a 1/10 second, you take every picture 1/10 second, then the exposure time between the frame is 1/10, right? So this here you collect more photon, here you collect less photon, because you have less time to expose your light sensitive device. So now if you do that, you will find your signal is here, but when you have a lower exposure time means you get a less photons. Then the picture become more noisy, right? So that means the signal to noise ratio goes down. So the n number reduce, then this signal to noise ratio decrease, and then here it becomes more noise around this source. You have many noise here. If you reduce the frame rate, means you increase the time between the frames, and then increase the exposure time. So within that exposure time, you can collect more photon. So the n number increase. Then you will find it's much higher signal to noise ratio. You have more. Your signal is here, noise is almost zero. But black means no noise. Okay, so people can do this experiment, use different frame rate. Then you actually put a hand into the outside of the window for different amount of time. Okay, sometimes you put if you put a very short time. You guys hear me? Do you hear me?
Yep.
Yeah, I saw Lola has a question. Okay, Lola has a question. How do we know that those processes follow distribution rather than other distribution? Good question. So the way is to find out whether that process is random or not. Poisson distribution is targeting the random distribution, random process, random events. Okay, that there are no history between no history remembered in those events. Okay, they are all coming random. Okay, so here, yeah, as I said, if we put the hands outside the window for always just 10 seconds, then the running job received by our hands, if you compare those received droplets, they actually have big variation, really big variation. If you always put the hand outside for a very long time, for 1 minute, another time you also put outside 1 minute, then the value, the number of the droplet you collected in the hand is very close to the time times the average value of the running droplet, because the variation become reduced. You put you expose your hand enough long, so then you approaching the average value now. Okay, if you very short time, then it can sometimes be higher, dense, sometimes can be sparser. Okay, so the fluctuation is very large. So that's the basis of the two applications of Poisson distribution. And then this one is directly related to that FX method, right? Now, yeah, here are more explanations that noise we counted there actually is called short noise. Short noise. It always it is named during the photo counting when you use laser photo counting. So here actually is one picture, one data. This is real data. This shows that when a laser is shining on a target, on a camera or on a photo detector, when the photo detector take the picture or take the measurement in different duration, for different duration means different exposure time, the photon counted, photon received will be very different. Okay, here on the top it shows you see here this is much in this one the y-axis is the number of the photon, on the x-axis is the time. Here you can see that at time 0 you have one spike here, means one photon. Here is a single photon counting, one photon, and then they wait for other time, and then at this time 0.01, around 0.01, you have two photons, right? Two lines very close by. And then after another time, no photon coming. And then at this 0.05 around, you have one, and then right after that, another two coming, and then another two. So within this 0.1 second, you get those discrete photon coming, okay? And then after in the next 0.1 second, you have different distribution, also counting the photon. Okay, every line, vertical line is one photon. You can see each 0.1 second time, the events is different. Events is different, right? So that means they are random. But if you count the average number of the spike within certain time, the average value will be the same. So this is a typical stochastic process, stochastic random process. Okay, so all these are happening. The random single photon get collected in the device. Now, if we count those number of photons we collected throughout that time, we can draw the histogram beams, right? Histogram beam. If we have the beam size 0.1 second, 0.1 second, okay? So then within 0.1 second, we find 10 photons. In next 0.1 second, we count about 7. And then the third 0.1 second, we count about 4 photons, right? 4 photons. So this first histogram actually shows that we count the photon every we count the photon every 0.1 second, okay? 0.1 second. Then we get this histogram, this distribution. Now, in this distribution, we can also calculate their delta change. This is the intensity, right? We can calculate delta change intensity versus the average value. We will find that this is about 10, square root of 10 divided by 10 is about 1/3, okay? So this is the reverse of the signal to noise ratio. Noise divided by the signal, okay? So 1/3. 1/3. Now, if we increase this beam size, we not counting on 0.1 seconds. If we still count, it's also fine. Here, this example actually is not in a time domain; it's on the space domain. If time is still the same, but if we zoom out the view, then we can have larger space to count the photon. That is equivalent to this diagram that increase the time, but we do not increase the sensor's space. Sensor space is the same as number 2, but we increase the time. These two are equivalent. I write here two different things. They are equivalent, but I want to explain that the space and the space domain and the time domain, in this case, they can be exchangeable. So if we look at this histogram, just in a time domain, now we increase the time 10 times. Every 1 second, we count the the photon number, then we can get about 100. Second, another 1 second, we get about 90. Okay, and then third second, fourth second, fifth second, then we get this distribution. Now, in this case, we can also calculate the standard deviation noise divided by the mean value signal. Then we can get every time we get 100, square root of 100, that's the standard deviation, right? Square root of 100, and then divide the mean 100. Then we get 1/10. Remember, this one is the inverse of the signal to noise ratio. So then this signal to noise ratio is 10. This one signal to noise ratio is 3. So this actually is the example showing to us that when we have those stochastic process, if we reduce our sampling number, either reduce the size of the sensor or reduce the time that we collect the data, we get more and more noise. Okay? And that noise cannot be beat. That noise always there is a physical limit. Okay? At some point, noise and the signal equal to each other. Then we cannot tell what is signal, what is noise. That is the limitation that beyond which we cannot do very meaningful imaging using the conventional way. Then we have to use some unconventional way to break that limit. Okay, that is also possible. Okay, now with this, then we go back to our facts experiment. Now you can understand if we have. Do you guys see my slides?
Yeah.
Yeah. Now we can understand that if we measure the intensity, fluorescent intensity of those molecules within this limited domain, now we get these fluctuations. By measuring the mean value, we will get the mean number within this domain, right? And then by measuring the fluctuation, we can actually get by measuring fluctuation, in fact, you don't need to measure. In fact, if you know the mean, then you can find the square root of that mean actually equals to this fluctuation. So they are matching with each other because all this process of those molecules getting into this beam volume, light volume, is following the Poisson distribution. Okay, so this is a link together. There are other principles also linked. Now, there are other things very useful to measure using this method. That is, we can also measure the diffusion coefficient within this of the molecule. Okay, using this method by measuring the intensity of the light. So because the duration of those fluctuations is proportional to the time it takes for a molecule to diffuse across the laser spot. So if we given any geometry of a laser spot, we actually can calculate diffusion coefficient. We will know the volume of the light volume here, and also we can measure the time. We can measure the time that the molecule has been inside this volume. Okay, and then by knowing the diffusion equation, we can calculate the D. Okay, so in the practical, you can use the way I just mentioned. And before doing that experiment to measure D, always people want to recalibrate the volume of the light and using a molecule that we already know the diffusion coefficient, and then to recalibrate the volume, light volume here. Okay, so here shows one example. So here is the freely diffusing molecule in the water, and then the light will form this cone shape. Okay, cone shape, and then the molecule for using the Brownian motion get inside and then go out. And then because this molecule, we know their diffusion coefficient, and in this case we also can estimate the laser's diameter and the volume of this light. Okay, and then measure, and then we using that we can calculate the time. In this case, you can calculate the time to do the calibration. So the distance you can put the distance in following a diffusion equation, and you put the distance in, and then put diffusion coefficient, no diffusion coefficient in, and then you can measure the time should stay in there. And then this time can be used to calibrate your device, your time recording device. From there, you can adjust your device to match this value. Once you matched, then you can put other molecule that has an unknown diffusion coefficient into this system, and then using the equation in a reversed way, calculate the diffusion coefficient. Okay, so the results, what you will find in the recording end in the device is those spikes. Those are different particles getting into the volume, light volume. Okay, and then from there you can calculate the meaningful information there. I also have more slides here. Actually, those slides also show in the homeworks, so you can use that. They have other things, other more sophisticated analysis you can perform to analyze the facts results, that fluctuation results, that you can get both the diffusion coefficient as well as the density of the chemical. So you can find out the concentration of the chemical using these methods. Okay, we can talk about this in next lecture. And then after that, and also the quotients. After that, we can talk about the expansion of the diffusion coefficient. Okay, 356 now. Let's stop here. Thank you. Do you guys follow me?
Yeah, it says so.
Very good.